So basically, this video is a continuation from our organic, the first year. We'll be talking about carboxylic acids and esters part. Now, basically, before this, we have been talking about the carbonyl compounds, on how obviously the formation of the ketones and the aldehydes from the oxidation of primary and secondary alcohols. This is undertaken by the catalyst, which is a strong acid catalyst, along with preferably a reducing agent, which is obviously performs the function of oxidation. That could be our potassium dichromate, which is our K2Cr2O7 respectively. Now, we also had a look about the reduction reactions on how the use of our oxidizing agent. For example, it can be sodium tetrahydride or borate or lithium aluminium hydride, which leads to obviously if we do in the case of an aldehyde, leads to the formation of a primary alcohol, but if we use it in the case of a ketone, it leads to the formation of a secondary alcohol respectively. Now, moving on to our carboxylic acid, basically how a carboxylic acid's formed. Now, if you recall that when we took our primary degree alcohol and we converted it into our aldehyde, notice that I told you about the distillation process. Now, basically, this distillation process was done to prevent the complete oxidation of the compound to form a carboxylic acid. Now, since we want to form a particular carboxylic acid, we want to allow the complete oxidation process to take place. That's why we use the reflux process. This is done under the heat or warm temperature. Basically, it tells us in this chapter how to name a carboxylic acid. We know that it has the suffix of oic. In other words, like if I say propanoic acid, for instance. And basically, that how is it what's it basically part of? Well, it consists of two functional groups, namely the carbonyl group, in other words, the C-double bond group, obviously found in both the aldehydes and ketones, and it also possesses the hydroxy group, which is found in the alcohols. Now, basically, due to the presence of these both two groups, this changes obviously the properties of each group. That basically, in the case of the OH group in the carboxylic acid, is more acidic than the OH group in consideration with the alcohols. You'll also see when you come under the infrared spectrometry, you'll also see the wave numbers differ completely when it comes to the OH in the alcohols along with the OH in the carboxylic acid. Now, basically, we come on to our physical properties of the carboxylic acid. Now, basically, carboxylic acid, due to the presence of these OH, you can say molecules here, they have the tendency to perform the hydrogen bonding, and therefore these form a polar solvent. In other words, these are polar solvents, and they relatively form the hydrogen bonds with the water molecules, resulting in them being able to be dissolved in water. In other words, they are soluble in water, so their solubility in water. They also, as I was telling you about hydrogen bonds with another in solid state, therefore they have a much higher boiling point than the alkanes of similar relative molecular mass. In other words, this is very, very important. They will ask you to compare the particular molecular mass with the case of these compounds. On that, this will have the highest boiling point and the melting point, respectively. Moving on to now, we're going to discuss about how to identify the carboxylic acids, to basically measure the melting points and compare them with tables of the known melting points. This is done in a Thiel tube. I'll just write down the spelling of Thiel for you. This is done in a Thiel tube. Basically, what acetyl does, it's basically in this particular shape, and this measures the particular melting point of the carboxylic acids, and like I said, that we will compare them with the table. Now, this is formed that how our pure ethanoic acid is sometimes known as the glacial ethanoic acid, because it may freeze on a cold day. And obviously, freezing point is 13 degrees Celsius, for instance. So our pure ethanoic acid, which is also known as the glacial ethanoic acid, can freeze actually quite quickly. Now, acids actually have a characteristic smell. For instance, as we know in the case of vinegar, vinegar is basically a 2% solution. Basically, vinegar is a 2% solution of our ethanoic acid in water. Also, as you can see, butanoic acid actually causes the smell of rancid vinegar. Now, as you can see, that in the case of our other compounds, which are the hexanoic acid and octanoic acid, are actually known as capriconic and caprylic acid, respectively, for the same derivation as practicum, the goat. They are present in goat fat and causes unpleasant smell, hence the name caproic acid and caprylic acid. Now we move on to the esters, basically how the esters are named. This is known as the alkyl alkanoate. Now this alkyl bit comes from the alcohol. The alkanoate, the O8, comes from the carboxylic acid, or the carboxylate ion, you can say the carboxylic acid. This is basically what we had discussed last time as well, that how the use of the particular the hydrolysis of the basically the formation of esters. Here, as you can see, this undergoes the esterification reaction. This undergoes the esterification reaction. And then we see the hydrolysis, which is technically the opposite, which leads to the breaking down of the ester bond, leading to the formation of, the reformation rather, of our carboxylic acid and our alcohol. Now basically, we now come to, as we talked in the last video about the use of esters, the formation of our, from triglycerides, the formation of propane 1,2,3-triol, which is known as our glycerol usages as well. Glycerols are used in the pharmaceutical companies. They are also used in the making of many drugs. They are used in the cosmetic industry, and they also use as plasticizers. Now, the use of them in plasticizers, they actually loosen the bonds, you can say, between the molecules, as these molecules are often the addition polymers. Now these addition polymers, for example PVC, normally they are quite, you can say, brittle. In other words, due to their structural arrangement, they are sometimes quite brittle. Now, to prevent the, or should I say, to increase their long-lasting nature, rather, to make them a little bit more flexible, the addition of the plasticizer is added to loosen these bonds. You would have studied about vulcanized rubber as well. That's something similar. Now we see here in the case of our as I told you already, for all of these food colorings as well, as you could, there's 50%. Biodiesel is also very, very important. How we form our biodiesel. This is a very, very important exam type question, actually, you can say, that can come. Moving on to our next part, which we'll be talking about, is now our I think we talked about the alkylation reaction as well, how the Friedel-Crafts alkylation reaction takes place. We also have this table in front of us, which we have to revise. And we talked about the use of alkylation reactions as well. Now, quickly, I'll be moving on to your aromatic chemistry part. Basically, in aromatic chemistry part, we're talking about arenes and the natures of the particular arenes. And in the arenes, we will be talking about basically the Kekulé structure of our carboxylic acids, of the benzene molecule. And in this, we'll be talking about various basically we'll be talking about the bonding in the benzene ring, on how the bonds are formed and why the proposed structure of our cyclo 1,3,5 triene is less stable as compared to the current benzene ring molecule, in other words, the Kekulé structure molecule. We'll also be looking then at the processes of, in this case, we'll actually be talking about the Friedel-Crafts alkylation reactions, actually, because you have talked about it in the last part, which we had just discovered, about the use of the alkylation reaction, obviously being relatively cheaper, it's less corrosive, it does not react with water readily as well, and it's safer for its obviously byproduct than the ethanoic acid. Is ethanoic acid rather than the hydrogen chloride, which normally is observed. So basically, we will be discussing then about the basically the arenes chapter. So this is what we see about the original benzene. As you can see, it's a ring structure. So this is our benzene ring structure in front of you. This is our benzene ring structure, and we'll be talking about a bit about of its bonding and its characteristics. Now, basically, this is also very, very, which I'll be talking about. Now, it says in this that the bonding and the structure of benzene ring was a puzzle for a long time to solve for, obviously, the organic catalysis, because in spite of being unsaturated, it does not readily undergo the addition reaction. We know that unsaturated compounds undergo our nucleophilic addition reactions, the electrophilic addition reactions. We know that they undergo, so the addition reactions. Now, however, that all the carbon atoms were equivalent, which implied that all the carbon-carbon bonds are the same. Now, basically, what is benzene? Benzene consists of a flat, regular hexagon of carbon atoms, each which is bonded to a single hydrogen atom. The geometry of benzene is basically this. Now, the difference between the flat benzene ring and the slightly puckered cyclohexane molecule you can observe in this case. The CC bond lengths in benzene are intermediate between those expected by the carbon-carbon single bond and the carbon-carbon hydrogen bond. This is basically an intermediate. Now, the symbol obviously this. Now this is where they can ask questions about, definitely from this part onwards, and obviously asking about the alkylation, Friedel-Crafts alkylation reaction. And basically we're talking about that it can be explained that the idea that some of the electrons are delocalized. Obviously due to the p orbital, electrons are delocalized, which increases the electron density. This is what we know. But according to the book, it says delocalization means that electrons are spread over more than two atoms, in this case the sixth carbon atom, to form the ring. Each carbon has three covalent bonds, one to a hydrogen atom and the other two obviously to the carbon atom. The fourth electron in the carbon atom is the p orbital, and there are 6 of these, one on each carbon atom. The p orbitals overlap and the electrons in them are delocalized. They form a region of electron density above and below the ring. Overall, each carbon-carbon atom is an intermediate between the single and double bond. The delocalized system is very important in the chemistry of benzene and its derivatives. It makes benzene unusually stable. It's sometimes called the aromatic stability. This is the evidence, as you can see, what I have portrayed, what I had actually told you in the beginning. In the case of cyclohexene, the standard enthalpy change of hydrogenation was actually minus 120 kilojoules per mole. So it would be expected that for benzene, the cyclohexa 1 1,3,5 triene, that it would be 3 times this number. But actually the structure by Kekulé actually led to it being 152 kilojoule per mole less, giving the answer of our 208 kilojoules per mole, proving to be more stable. As you can see in the diagram here. Now when it comes to the naming of the arenes, this is a part of the Kekulé structure that he had added in this case. Now we come to the physical properties of the arenes molecule. Basically, benzene is a colorless fluid at room temperature. It boils at 353 Kelvin and freezes at 279 Kelvin. Its boiling point is comparable with that of hexane, but its melting point is much higher than hexane's, which is 178 Kelvin. This is because benzene's flat hexagonal molecule are packed together very well in the solid state. They are therefore harder to separate, and this must happen for the solid to melt. Obviously, they have to break the bonds in order for the solid to melt. Since these bonds are particularly more, due to the flat structure, they are more stronger. It takes a larger amount of energy and hence a larger melting point. Now, naming of the aromatic compounds, you know that this is equal to the methyl benzene, or you can say this is known as the toluene as well. This is referred to the chlorobenzene, and obviously this one for dichlorobenzene. You'll also get this compound in the Friedel-Crafts alkylation reaction, and it trips up many people, the naming of this. This is known as the benzophenone. Okay, now we see the reactivity of the aromatic compounds. Basically, the two factors which are important to the reactivity of the aromatic compounds. Basically, the ring is an area of a high electrodensity. And as it has a high electrodensity because of the delocalized bonding, and therefore is attacked by the electrophile. So this undergoes the reactions of the electrophilic substitution reactions respectively. Now, meaning that electrophile, we know our particular electrophiles in this case, which are the NO2, the H2SO4, and the H positive respectively, which is where we come on to the reactions of the nitration reaction, which you should know that this undergoes the presence of the concentrated sulfuric acid plus the concentrated nitric acid leads to the formation of the nitro compound. These are being the catalyst. And as you can see, the reactions displayed in front of you are such of the reactions which prove that the NO2, that prove that the H2SO4, in other words, the concentrated sulfuric acid, is in fact a catalyst, as it is formed at the end of the reaction. Now, basically, you can see in this case that upon how the formations of the combustion reaction takes place, that basically when burnt in air, the flames are noticeably smoky. Why? Because of the long chain unsaturated, obviously being unsaturated, they have a high carbon to hydrogen ratio compared with alkanes. They are usually unburnt carbon remaining, and when they burn in air, this produces soot. A smoky flame suggests an aromatic compound. Now, this is basically the nitration reaction, and we come to the use of them. Now, basically, nitration is an important step in the production of explosives such as TNT. Nitration is the first step in making of the aromatic amines, and this in turn is used to make industrial dyes as well. Now, I don't know whether you can see this, but this is the explosion of the TNT. I'll just write out the TNT molecule for you here. Now, this basically reacting with the 10.5 molecules of oxygen produces 14 molecules of carbon dioxide, 3 molecules